All right, we'll finish up this topic 7 worksheet now. I just had 2 more problems left to go through. Problems 21 and 22 are some application problems of exponents and logarithms. So let's take a look at these now. Problem 21, bismuth 210 decays according to the function which is given there, a of t, where a sub 0 is the initial amount present and a is the amount present at time t, which is in days. Assume that there is an initial amount of 10 grams of bismuth 210 in a sample. Now, the first thing that I notice here is that the exponent on this function is a negative. That means that over time, there's going to be less and less bismuth 210 in the sample. Okay, like we're starting with 10 grams of this stuff. As time goes on, there's going to be less and less of that there. So, part A, we want to know how much bismuth 210 is left after 1 day. Well, t is the time, which is in days. So that's just going to be a plug it in and simplify, right? If I do that using my calculator here, I've got 10 times e to the power negative what was it? 0.139 times 1, and we get 8.7 grams. That's what I'm getting there. Okay. Part B, how much is left after 1 week? So same deal, you'll plug in the number, 7 days in a week, right? So let me retype this, and of course I want the exponent to be in parentheses, that entire thing. If you don't have the parentheses there, you're not going to get the right answer if you're typing in the whole thing all at once. Okay, so t is 7, and it looks like 3.8 grams are going to remain after 1 week. Okay, how much are going to remain after 2 weeks? T is 14, so again, just change that t value to 14, and it looks like we get 1.4 if we go nearest 1 digit on that. Okay, so you can see that over time, there's going to be less and less bismuth 210 in the sample. Okay. Part D, what is the half-life of bismuth 210? In this problem, we want to know how long are we going to have to wait until we get down to half of what we had started off with. We're starting off with 10 grams of this stuff, like when is it going to be at 5 grams? Well, it looks like it's going to be less than a week to be at 5 grams, right? Because at a week, you're already at less than 5 grams. But I would just set the amount, a of t, equal to 5, and then solve for t. Let's do that now. So divide by 10. 5 over 10 is 1/2. The bases are not going to match here, so you'll want to take the ln of both sides, and that allows you to pull the power in front of the logarithm on the right. So on the right, you're going to have negative 0.139t times the ln of e. The ln of e is 1. Divide by negative 0.139, that way t is all alone. And then go to the calculator and type in ln of 1/2 divided by negative 0.139. And I'm getting, looks like 4.987 if I go nearest 3 digits on that. Days, the time is in days here, so I'd want to include the units there, of course, in my answer. And just as we expected, you know, this was less than a week to get down to 5 grams. Okay, problem 22 is the last problem I had on this worksheet here. The number of cells, N, of E. coli bacteria present in a culture at time t, which is in minutes, obeys the law of uninhibited growth according to the function n of t. Notice how that the exponent is a positive, so that means that as time goes on, there's going to be more and more E. coli bacteria in the population. Okay. Part A, what is the population after 15 minutes? Well, t is the time, which is in minutes, so I would just simply plug in 15 into the function and simplify. Let me do that. I'm going to have 5,000 times e to the power let's see, here it is, 0.05, 0.035 times 15 minutes. And I get roughly 8,452 cells if I go nearest whole number. Okay, part B, when will the cells double? 5,000 is the number of cells that are there at time 0. So when is it going to be double? Like, when is it going to be 10,000 cells? Well, it's going to be more than 15 minutes, right? We can see that from part A. But I would just set n equal to 10,000 and solve for t. Let's do that now. If you divide by 5,000, 10,000 over 5,000 is 2. The bases are not going to match up nicely there, so you'll take the ln of both sides. On the right, you can bring the power in front of the logarithm. 0.035 times t times the ln of e. The ln of e is 1. And you can divide then by 0.035 to get t all alone. And then go to the calculator. ln2 divided by 0.035, if you were to check that, would be 19.8 roughly. Okay, so yeah, just as we expect, a little bit, more than 15 minutes to be at 10,000 cells then. Part C, what is the population after an hour? Well, the time is in minutes, okay, so there's 60 minutes in an hour. And so I would go to the calculator here and just make the time 60. And it looks like we'll have 40,831 cells if we go nearest whole number value on that. That's how much would be there after at 1 hour. And then part D, when will the number of cells be at 100,000? So n is the number of cells. So you just set that number equal to 100,000 and solve for t. Okay, divide by 5,000 on both sides. 100,000 over 5,000 is 20. And here's another situation where the bases are not going to match, so you'll want to take the ln of both sides. Now, if I compare this calculation to what I just did in part B, really the only change is going to be in the numerator. Instead of it being ln2, I'm going to have ln20. Okay, ln20 divided by 0.035 is roughly 85.6 minutes if you go nearest one digit on that. Okay, so of course it's going to be more than an hour, right? To be at 100,000 cells, we can see what it was at 1 hour. So this at least looks correct. Of course it is correct though. All right, at this point we're now done with the topic 7 notes, and be sure to look at the homework that is online and the homework that is in the 115 book.